So I'd like to use this presentation. It's by Full. They're a metal panel manufacturer. And so this is for AIA continuing education. It's nice to have the contrast that they're a metal panel manufacturer because I presented in the previous part of the lecture these terracotta panels. So this is kind of a little bit of a contrast or another viewpoint. Also, just to keep in mind, this is a viewpoint of a metal panel manufacturer. So some of their commentary about Rainscreen systems might be more leaning towards the advantaging themselves as metal panel manufacturers, just to keep an open mind about what you see and what we talk about. So I'll get right to the table of contents. Wall evolution, we're going to talk about how we get to where we are with Rainscreens, some of the kinds of design principles that guide that, and then the kind of design details and how they play out in wall systems. And I'll just touch a little bit on the features and benefits in this presentation because I think they're not really well developed in this slideshow. So wall evolution, this is just seems to be a totally inappropriate image for this, but the idea of water penetration, one of the primary concerns with building wall assemblies, right, to keep us dry. And typically the idea was that the drainage plane, the exterior was the ceiling point. And so our construction of walls kind of developed around that idea. So here we have a brick constructed wall with a CMU. So the blue is the air on the outside, the beige is the brick, the gray is the CMU stacked up, and then there's a little line, and that's kind of the interior plaster coating. And this is typically how buildings would have been built in the 50s. Very little insulation. We're very little concerns about energy use. We could heat our buildings very easily by consuming large amounts of fossil fuels. And in the summer, we opened windows to cool them, at least in the Northeast. So it really wasn't, and the expectations of air conditioning were very low, so no one really complained about it. This efflorescence that they talk about is the idea that moisture is migrating from the inside of the wall, hot, warm, moist air, pushing through to the outside to cold and driving moisture through it, and then the calcium coming off of the brick and running down the face surfaces, making kind of a white staining on brick, which you'll see many times if you pay careful attention to brick assemblies. And it can be an indication of a problem with the construction, and sometimes it's not. It's just a natural effect or problem that comes with the type of construction. So in the 60s, we started to tighten up wall construction. Now you see us adding this insulation in, and this is just one part of a story of an evolution. There's a lot of there's a lot going on in the evolution of wall assemblies, and this is not the only part of the story, but it's a nice concise story to help get us to the point of where we are at Rainscreens. So here we add insulation, and we needed to add ways for water to get out. Weep holes. We started to think about barrier systems within the cavity, and actually things weren't actually too problematic at this point until we arrived at the 70s. And in the 70s, we really have to tell the story about energy. So prior, in the prior years, all the way through our industrialization, fossil fuels was relatively plentiful, and we had no concerns about them becoming scarce. In the 70s, we became very aware, especially when we started to deplete U.S. resources of energy, that we were coming to a crisis, an energy crisis, and that had political implications to it, and the whole idea that we were getting our fossil fuels from the Middle East, our oil and petroleum were being imported into our country. And so the price of energy started to climb very rapidly, and people became very aware of what it was costing us to heat the interiors of our buildings. And there was also this idea that resource was a diminishing resource. Back in the 70s, it was estimated that we had about 70 years of oil supply and maybe 300 years of coal supply. Those are the kind of numbers that I remember as a young student. And so we thought in our lifetime we would be running out of these, at least of oil. It turns out, to tell the story to today, that through better techniques of exploring and identifying oil reserves and better ways of extracting oil and gas, like for instance natural gas, we now have fracking, which is an environmentally damaging way to extract, but nonetheless a way that we use to extract natural gas from our earth. we really changed the idea that we have enough fossil fuels to really do all kinds of untold ecological damage and create a much tougher future scenario with respect to global warming. So it's not now today that we want to reduce energy use because we're conserving a depleted resource. It's because we do not want to suffer the impacts of climate change. So anyway, that's an important part of that narrative because back here, the talk about energy is different than it is today. But nonetheless, the solution sets are very similar, or the ideas of how we got to where we are, all driven by this idea of conserving energy. So the first low-hanging fruit with conserving energy was to deal with the loose construction of buildings. Up to this point, air change per hour was very little concern because we could reheat any incoming air through drafts or whatever. And it was the low-hanging fruit of knowing that this existed that was our first way of starting to increase energy performance in our buildings. So we started to seal up openings, caulk, tighten around our windows, look at all kinds of places where we could keep air from moving from the inside to the outside. And as a result of that, because our building wall systems weren't created necessarily to accommodate these issues, these ideas of mold and mildew damage kind of went up, and mold-related lawsuits and problems with the healthy quality of interior air environment. And I want to say that's not the total story. It's not like, oh, we all discovered it was mold and mildew damage and we all needed to do something different. These are parts of a bigger story to the evolution of where we are today, thinking about more advanced high-performance wall construction. There were other problems with sealing buildings too tightly, and that was indoor air quality in general. So, you know, that kind of history, that really brief little chunk of history, gets us to this idea of where we are today, or where we're evolving to today, with the idea of Rainscreen wall construction. And this illustration that's behind me seems to be totally inappropriate to that, because this seems to be a screen system, a double-walled screen system, but it's not a rain screen system to the best that I can determine. So don't be misled by that image when we start to talk about rain screen walls. And another seemingly inappropriate image. So the idea of rain screens is really about moisture migration from the outside exterior environment, rain and precipitation, to the interior wall assemblies. We're not specifically dealing with the moisture migration in the other direction when we talk specifically about rain screen systems. So we talk about the fundamental requirements for problems with water, right? A source of water, and opening a path for the water to follow, and a force to drive it. So, and that force to drive it could be capillary action, could be kinetic activity, it could be a pressure differential between the inside and the outside. Now, they don't tell you what that, according to the CHMC document, is, but that's the Canadian Housing something of Canada. And that's one of, what's important about that is it's one of the first documents that really started to discuss technically rain screen wall construction systems. And that was released back in the 60s or the late 60s. So this is when we're first becoming, in architectural design and building engineering, really starting to consider the concept of rain screen construction. Now, we're talking about back in the 60s, but it's going to be decades before, many decades before this becomes common parlance and discussion to designers of wall systems. And so that's why this idea of the historical changes in the industry, how long it takes for ideas to evolve, and also for mistakes to be realized. The idea that we're sealing up wall systems, we thought we were doing a really good job of it. It took a decade before we realized that we were probably making things worse with a lot of other issues in the performance of building systems. So let's deal specifically with a few of those forces so we can have some visuals to connect with it. This idea of a kinetic force, the wind-driven rain hitting a surface, bouncing off of it. You could imagine a heavy rainstorm, water hitting a table surface or a hood of an automobile, and feeling that mist that comes off from it. Even if you're under shelter, you can feel that air, that really small, fine droplet that comes after the splash, come to reflex back off again. And that's because that water droplet has a lot of kinetic energy. When it breaks into those smaller water droplets, they travel a great distance. And so this is a way for water to move into the openings between panel assemblies. So this illustration, just to point out what we're looking at here, we have the rain. The yellow is the exterior of the building. The gray is that interior airspace. The textured L-shaped piece is the cross section of the metal panel. And here we see that water being driven in by kinetic activity. And you'd say, well, we just seal up the gap, but we actually can't seal up that gap because we have to allow the panel to be ventilated, because that's one of the other drivers of moisture within these assemblies. So you'll see in a few illustrations, we're going to deal with that kinetic energy by the way we shape that panel. But another force that's going on is the idea of surface tension. I think we're all familiar with that. Water tends to adhere to the inside surfaces of things like a glass. Water is sometimes hard to see, but we know what happens with milk when it's poured along a glass surface. That idea of its attraction of a liquid to another surface, it's called a surface tension. And so once we have that surface tension, the water can follow that surface, and if that surface is directed to the inside of a panel system, it can drive water into the inside of the building. And so if we take surface tension to the next level, we have what's called capillary action. We take the liquid and put it between two surfaces that are very close together. We get an idea of capillary action. This happens in small cracks, in small openings, and in poorly designed panel assemblies. If the gap becomes less than, typically the guide is 1/4 of an inch, we have concerns about capillary action. And why I say 1/4 of an inch is probably, we still wouldn't get capillary action at 1/8 of an inch, although I'm not an expert on it. But in construction, in the construction world, if we're not starting with 1/4 of an inch, we have no way of guaranteeing that it will not get too small because of the tolerances. Some panels might be spaced as far as 1/4, they might go down to 1/8. So we really want to have a generous opening in order to make sure that when it's constructed, we're not generating that idea of capillary action. So we see that water coming to the top there, and it looks like it's really not getting into the assembly, but you can imagine during this, if this was a live video, that little bubble that was coming up would actually run down the outside, would bubble over and start to run down the inside of the panel and start to bring moisture to the inside of the wall assembly. So another mechanism, we have this idea of surface tension. Water moves along the surface, but when it forms a drip, we have control over where it's going to form that drip or where it's going to gather, and that's because we can control that force of gravity. In this case, the panel assembly is constructed exactly so that water would be driven in because the angles are going in the wrong direction. Obviously, if they were pointed up, the water would be driven to the outside of the facade. And I want to back up one frame here because we talked about this idea of kinetic energy. And the idea of why are these panels overlapping like this? And that is to create a baffle. So imagine that water gone and imagine kinetic water splashing on that. That L shape is a baffle that prevents that kinetic energy, that splashing of the water, from getting up into that rain screen. So they really should have, if I get a chance, I will make a whole new series of illustrations showing how, like for instance, the capillary or the kinetic energy is mitigated by creating this kind of baffling system, and to do a little bit of a demonstration of it or illustration of it. And then finally, we have this idea of the air pressure differential. And this really is probably one of the most important concerns in rain screen construction. The idea that when the wind blows on the outside, it creates a high pressure, a pressure higher than the inside, and that can force water into the assembly. But that's just one idea of the mechanism. When winds are at high speed, we can actually create high pressure on the outside of the building, and by moving the air fast along the outside of the building, we have Bernoulli's principle, which actually can effectively lower the air pressure on the outside of the building, so water could be forced from the inside out. And you'd say, well, that's not really much of a problem. Well, the problem is that what that does is that can actually pressurize the inside of the building. Wind is blowing by it, and the interior air pressure goes up. Goes up. And so when the wind pressure is relieved and goes back down again, or vice versa, the water can be driven both ways. So you can imagine this kind of pulsation of wind velocity. So we have fast moving wind, water driven one way, the wind recedes, water gets driven the other way. And it inevitably, this tends to pump water deeper into wall assemblies. So we're always, one of the primary concepts in Rainscreen construction is to reduce this pressure differential to stop that drive of water into the interior of the wall assembly. So these are relatively poorly constructed cross sections. This is why I started out with the Rainscreen assembly showing you it as a 3D version. So we're looking at a 2D cross section. The P1A, B, and P2 are the pressures. So we have really the same things now with just a simplified illustration. The Rainscreen veneer, obviously there's no gap illustrated. The wall cavity, which is white, which is really just nothing there. The insulation, once again on the exterior of the building. The structural wall that we showed previously is a metal frame construction, is now a concrete or a CMU unit. And we have that blue dotted line, which is the air and water barrier behind the insulation in order to create our wall assembly. So I think I've talked about all of those. Rainscreen. Let's talk about the idea of pressure equalization. I don't know if we have a good illustration of that. We go through 3 slides, and so I'm just going to talk about this idea that idea of pressure differential occurs at P1A and P1B. The pressure differential between those two pieces of panel and that gap between can kind of suck water into that assembly. And so the idea of properly ventilating it is what's called pressure equalization. And by doing it, if we vented it properly, if there's enough openings between the panels, we have very little pressure differential. P1A and P1B are equal to each other, and we don't have anything to drive that water into the interior of the assembly. And so that has a couple of other advantages. It allows the panel construction to be a little bit lighter because it doesn't have to support the pressure differential as much because it's pressure equalized. But mostly it is intended to reduce that idea of driving moisture into the wall cavity. So this is kind of where the discussion about rain screens and pressure equalized rain screens and back ventilated systems to me becomes a little bit murky and convoluted. And so I'm not going to actually answer that question. I think it's still up for, I guess, a really solid set of definitions about this. But back ventilated systems are just not dealing with pressure equalization at all through a theoretical method. They may actually be acting as pressure equalization systems, but the idea is that they're just ventilated in order to be to allow that break so that water can't reach the insulation, and then to allow enough ventilation for that insulation to dry out through the exchange of water vapor. So, but this idea of pressure equalized systems is really an advanced system, and I'll go forward to this illustration, and the idea of compartmentalization. So for a true pressure equalized system, we need to understand really at a level that's beyond our ability to calculate it. We have to kind of make some educated assumptions and really require expertise on this from facade consultants. This idea of a compartmentalized area that is isolated from the other areas. So those X's, that 20 to 30 foot by the floor line separation is a compartment. It's sealed, so it's that continuous airspace that's behind hits an obstruction at those perimeters, and those perimeters then prevent the movement of a pressure differential between those zones. So they're relatively large, they're floor to floor, so it's very easy to put a separator between the floors. And one of the things to really consider here is the pressure areas, the isolated areas, are really quite large. It can be up to 30 feet wide, which could cover the major facade of a building. But what happens is especially acute at the corners. So at the corners, during wind events, the pressure differentials, the wind speeds and velocities at the corners tend to accelerate. And so the compartmentalized spaces tends to be reduced when we get to the corners of the buildings. So they may be half. And they may be half because they're folded around the corner, and the corner has a baffle in it also. So just hold in mind that idea when we talk about pressure equalized systems, we're talking about compartmentalizing the certain areas of our large wall assembly. So we'll see some illustrations here. But one of the goals of Rainscreen systems, besides dealing with moisture, and this is like a second level of thinking, is the idea of energy efficiency. We can obviously build very efficient walls without them being rain screen performing, but by moving the insulation to the outside of the wall, we can create a continuous layer. As I illustrated in the HOK medical building, the insulation applied to the outside of the building, mostly continuous and uninterrupted, except for the placement of the Z-girts. Codes and testing. I'm going to save this for a whole other presentation about rain screen systems and wall assemblies. And then we're going to talk about some kind of maybe specific details in wall assembly systems, and transitions between areas in order to create continuity. So one of the first places is that transition from the wall to the roof. So here we have a typical coping detail. Once again, we're seeing the insulation to the exterior of the building. It's very common for roof assemblies to have the insulation on the flat roof of the building. But take note of the membrane that's wrapping over the top curve of the parapet and the relationship of the rain screen veneer. Think about that coping and how water would run down it and drip off that edge. How that is all in a, there's a capillary break by the amount of gap between the coping and the other parts of the assembly. That there is a somewhat of a baffling of, you can imagine water splashing on the roof, and how it would have a difficult time splashing deeper underneath that coping. So think about those mechanisms that we've talked about. Another and probably a more important critical area is the transition of the wall surface to the window surface. So here we have anchoring devices that we've talked about before. But what we have is that, in this case, it's a structural wall, precast concrete. And then we have that applied black air and water vapor barrier. And it's a vapor barrier in this case, which might indicate what climate it's being constructed in. And it would, if you look to the left, you'll see there's silicone sealants and a continuity of the air and vapor barrier. So even though the material looks black around the windows, there's still another vapor barrier that's continuing across that surface. The whole surface would be better illustrated if it all looked black. I don't know why that. I don't know why they use that image. This just shows, this is actually just a really helpful way for you to understand how membranes are attached to windows to ensure that the water flows around. So there's a set of steps. You do the left and the right, and you make sure that your last piece of flashing is over the top. So things are overlapping as if they were constructed as a shingle construction. So we would have, the bottom piece first, the two sides, and then the top. So once again, a transition to the top of the window. Really critical, complicated. You'll notice that it's not easy to see, but if you look at the red line, it looks like the water is dripping into that channel. But that channel is a U-shaped channel, so it could run down. It will run down the sides of the window and then exit at the bottom of the window. Will there be flashing to pull that back out to the front of the assembly? I think most of that is self-explanatory. This is actually a little bit problematic. This is just another illustration, probably mostly for, this would be really kind of a violation of some of the rain screen principles, because now we've moved the insulation inside of the wall, of the structural wall. And so any water that got through the membrane, the blue, and I'm not sure what they're calling it there. They're not actually air and water barrier, window assembly. They're not actually labeling the blue, but any water that got behind that blue would actually be trapped within that wall assembly. So this is what I would suggests is actually a poor performing or a poor design for what would be called a rain screen. And it's not to say you won't see a lot of this construction like this. So here we have it with the continuous insulation on the exterior of the building. And this is probably a better illustration of the continuous nature of it. In this case, the clip systems aren't continuous, so they're really not interrupting a lot of the insulation of the building. This gets into structural, so I'm just going to, I'm not going to, I'm going to move through it quickly, not because I don't think it's significant, but because it's just not germane to our discussions right now about rain screen systems. But we do have this idea, and we're going to cover this in another section, the idea of floor and roof deflections affecting our panel systems, live and dead loads, and so how those are transferred between assemblies. And so one of the reasons I think they put this in is because they make these panel systems and they need to deal with the connection systems that go along with them. But we're really no longer talking about the idea of the rain screen assembly itself. These are just the mechanical fastenings, which have this idea of thermal expansion, different loads, gravity loads or floor loads that might cause the deflection of the floor. And you can imagine a very flimsy floor with a lot of deflection, deflecting an inch in the exterior panel system, then having to absorb that deflection without popping a panel off. And then transferring the weight of that assembly down to the floor. And once again, this is just getting into the really technical details of this one, and they use precast concrete for this, and I'm really surprised it's for a metal panel manufacturer that they use this for an illustration. But here we have unitized assemblies. We're going to be covering this once again in the next presentation or the next module. So features and benefits. We're hoping these things last forever. I think that that's well within our expectations as long as they're constructed properly. But I think that idea of constructability is a really big ongoing issue. And it's one of the reasons I want to start you really seriously as architects thinking about it, because there's a lot of ways we can mess up these kind of wall assemblies. We've talked about the idea of thermal performance. Ideally, though, there are issues with thermal performance. We're limited in the types of insulation we can use on the exterior of the buildings. If we add insulation on the exterior and the interior, we have to deal with wall condensation. So rain screen systems, while they do offer some opportunities for better thermal performances, they can actually add some extra complications for thermal performance. And I guess I like this one about the aesthetics just because it's discussing that we can make these panel systems out of many different kinds of materials. And I think they have another slide that talks about that. This is really marketing long-term cost savings, maybe less maintenance. Certainly you don't have to go and seal because of failure of systems. Just once again, a little bit of a marketing. Options for rain screen cladding, once again, stone, metal, ceramics, terracotta, glass, zinc, wood, recycled man-made materials. And they have a few case studies, and these case studies are really directed around some of their metal panel systems. So I'm going to conclude that presentation. I hope it was enlightening for you.